Alright, if you are me, it's been approximately 2 minutes since the last video. And, yeah, if you're not me, well, it's been an indeterminate amount of time. So, monads are not that complicated. And, like, this is another thing, they're really cool, I will say. It is really cool to think about what a monad is, but to say they are complicated is not at all true. They are beautifully simple, is a more accurate way to think about it. And why I say that is, like, I've had discussions with friends about, like, what's a monad, what does it really mean? And it's not even any really different from what a functor instance is. And, but theoretically and, like, and just in practice, like, what a monad is, I guess you could argue it is, like, more, philosophical, I suppose. Like, it's, so, and I'm kind of getting stupid here. I would say it's a great implementation of what context is. And so, like, a computer can't understand everything, but I feel like a monad is just like a computer's way of thinking about context. And that's often how I see monads are used, and I guess this is not exactly true, really, but there are certain libraries, which I will not mention, that I think make a very nice use of monads in in real practical examples. And there's definitely real practical examples for fmap and for applicative, but it is just so easy to think about stuff with monads. And the easiest example of that, or the kind of point where monads really click, and, like, sort of like a functional sense for my brain, was when I did parsing. And so I encourage you to kind of keep your eye out for that video in case I don't do a perfect explanation of what monads are. Yeah. So and so now let me talk about monads in a functional sense. I would say, like, I would think of monads like this. Like, if you had, let's say you had a pipe, like a plumber's, like, we're plumbers, and we are building a pipe system. I would say that monads are kind of like that. And so, we could have our pipe, we only have pipes that are about 3 feet long. And we can connect these pipes. So, pipe 1 can feed pipe 2. And, it's still in a pipe. It's just further down the line of these pipes. Right, and this can go on and on. I'm just going to do that. And I'm going to... Right, pipe 3, so on and so forth. And we can keep chaining these pipes together. But, we also have the ability... We have these kind of special pipes. And these special pipes kind of look like this. In the sense that, and I'm a very visual person, if you can tell, and all these underscores are pipes, just like this kind of, one underscore is kind of equivalent to this statement here. This is pipe 1, this is pipe 2, this is pipe 3. And we can just have these other pipes which can come into our main pipe. And so, yeah, but it never, we wouldn't want our water to leave the pipe, I suppose. And that's a very icky example, because it's like, okay, what does that have to do with programming, man? But we really don't want, I mean, it is true, we don't want our values to leave this context. Now, and we might want to, we might want them to leave the context, but I really hope that it's at the end of the pipe. Wherever we're trying to transmit this water to, or transport this water to, yeah. But along the ways, we can have inputs to this pipe. We only want one output of this pipe, and that's all the way at the end, but we can have multiple inputs in this pipe. And so, now in Haskell land, like, what is a pipe here? Well, we'll come back to that. An easy example of bringing into the I/O monad, for instance, because, again, you might recall that I/O is the OG monad, the original monad. And so, what does like an internal kind of coming into the pipe look like? And there's two things that come to mind, and I'm not sure where I'm going with the second, but the first one is, get line. And get line goes, sort of outside of our nice, type safe monad that we've defined and designed, and it goes out into the real world and it grabs some value and it returns it into our monad. And so, I mean, that's kind of a way in which we are bringing into the pipe. And so, keep in mind with all this, I'm just sort of setting the stage about how the monad type class works and what we're doing with monad. The other case in which we can kind of bring something into the I/O monad, we can do anything that is pure and bring it into a monad. Like, there's no reason I can't, find the square root of 100,000 and then use it to affect, down the line. And so that, I'm not sure if people normally think of that as a coming into the monad type action, but, I could say, pure, which we saw from the applicative type class, and it's bringing into that wrapper, right? It's wrapping in I/O. I could say this is pure, is of type I/O a. This is the type of it, and a valid case or a valid instance of pure, or a valid instance of applicative is the I/O monad, and so this type checks. And so, I could do some, this A could be the result of doing some crazy mathematics, and then I just bring it into I/O. And, for some reason I want to do that. Now, what else is there? Well, okay, we're not just going from out of thin air to another pipe. We're going from pipe to 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 pipe. And so, we need a way to model this sort of passing from pipe to pipe. And so that's where we get our, that's where we get this function. And so, kind of looks cool too. I just like the way it looks. This function here is the core monad function. So if we look at the info of the monad type class, we see there are two main functions which matter here. And so they're very well, they're kind of they're opposites in a sense. And not directly opposites, but we'll come back to that. So this function here, this looks complicated because we have and I think this is like where a lot of people get really confused, is we have this function here, and it has an MA and some function. Just think of it as some function for now. Don't even dive into what the heck this is actually saying, because, it's kind of confusing. So, this is why I use the pipe analogy, is that we're passing from pipe to pipe. You wouldn't want leakage out of the pipe, and, you might want some controlled coming into the pipe, but that's not what we're even trying to model here. We are using this function is effectively the relationship between this pipe and this pipe, in a sense. And yeah. So, and I think that's best done with the example. So here's what we could do with this function. So you guys know getLine. We have our type of getLine, and we have our type of putStringLine. And I'm going to use putStringLine over print just to make it really clear what the heck is going on. And so I have my function getLine, and then I'm going to pipe it into the function of putStringLine. And see, this just type checked, so this works, this is valid, and let's say hey. And so it types out hey. And we know this actually did something here, because if I do getLine, we have these ugly, double quotes. Here, it's doing putStringLine, it's doing putStringLine, and so we don't have those double quotes because it doesn't go through any show instance. The REPL, just to deal with any sort of inputs that you have in there, will just do print of your final output. So this would get line and get some string, like I could do, for example, and this doesn't print anything, but now if I do X, it's going to show it, because I'm finally asking it to print, whereas if I just do this, I'm not saying it to a variable, and so it's just going to print it out, and that's just like how the REPL works, right? But here, I am clearly doing something, and I am, what I'm doing is I'm getting the line, or, like getting from standard input, not foot, and then what am I doing exactly? What is this function doing? Well, let's think this through in types. So we have our type of getLine. We know that this function type checks so that these type variables all make sense, and we have our type of putStringLine. So which is which? Well, okay, what is M? Our M is IO. Okay, so let's fill in the blanks a bit. Do we have an IOA in the equation that we just built? Yes, we do. Get line. Okay. So then it's fair to say that this was IO string. And if we backtrack a bit before I did that, we notice that this A is the same type variable as this A. And now, that doesn't in the general land of type message or type signatures, that doesn't mean that it is the same. We could do some weird stuff in the middle. That just is why. But in the case of monad, I guess I also do know, but I would be also wise to guess that this A is this input A to this this function I have passed here is coming from this A. And so what's happening under the hood is that I am unwrapping this A from the IO, and I am feeding it to this function. And this function is going to return an IOB. And so you might also be confused by, like, okay, well, if this returns an IOB, then what the heck is this? But like, we had a function earlier where it was my funky funk, and I think it's still here. Is it? It's here. And we didn't really question that because maybe you guys questioned that. I guess I don't really know. I don't know. Maybe we did question that. And so here we can see that, this function is going to give us B. And that's going to be our return type. And this makes complete sense. I mean, we could even do another thing, or we could say maybe B, and this is a maybe B. And we could make this type check by saying, I guess func would be, I was going to put a just there, but if func returns a maybe B, then this is going to evaluate in place, and I can say for sure that the type of this is maybe B, which corresponds to the promised type of the function. And so in the same sense, that's why this IOB, makes sense for, the relationship between these IOBs and this IOB in the function that we get. And so just a bit of Haskell terminology, we would say that this is a monadic function, in that it takes some plain arguments and returns IO, and returns something wrapped in that IO context. Technically speaking, too, something like this in a different type signature could also be a monadic function. And so it will still actually end up fitting this, because as we apply and apply and apply, we end up with eventually this. And so this still fits into being a monadic function, even though it had more arguments. And so, obviously now if we were to go one further, because you might be thinking of getLine still as a function, when it's not. It's really more an IO action. Gosh, get it right. It would not fit this type signature. And that's just, plain old type signatures. It has nothing to do with monads. It just would not fit. And so, yeah. And so, this monadic function, or the, I don't know, what do we want to call this? Piper? Yeah, we'll call it Piper. I just kind of, look at it usually, but we'll call it Piper. And if Piper, so Piper is meant for a very specific use. A function is not supposed to do everything. It's supposed to do a very particular thing, and it's supposed to just kind of continue through the monad. And this is very chainable, because let's say this is fully applied. So we have getLine. Well, even too. So here's how I could do this. Here's how I could show this very quickly. If we look at the type of this, it's also an IOA. Now it's kind of a useless IOA because it gives us back the unit, but nevertheless, it is still a. I would have to do this. It is still a, something that would fit. And so we can see that fully type checks. And now let's run that. And what we're going to see is we are going to input some random characters. It's going to print back out those random characters with no quotes. And then it's going to print out the unit. Voila. And I suppose we, come to think of it, I've never done this because this is just madness here, but we could do this. And there's no reason we couldn't just continue on doing this. This is madness. Oh, man. And, what are we going to do with a unit? That we've kept a unit in our IO monad. It's not really useful, but yeah, it's not, we're not always going to do put string line all the time. In fact, we might have something like this. This is more accurate. We might have a function which gets this string input and does put string line, and then we're going to introduce our other operator. Well, I have to do that first, but we're going to introduce our other operator, a put string line string input. Hey. So what's going on here? So this is still, in case I haven't explained very well, this is anonymous syntax, anonymous function syntax. So a function without a name, in this case, the function takes a singular input of string input, and that's going to come from this getLine. For example, and why I can do this is because this function here is expecting a singular argument. And so it might look a little hectic. I mean, even to me, it looks a little hectic in terms of how this sort of evaluates, because I don't really code like this ever. There's an easier, nicer looking way to do this. But yeah. Anyways, this is, just to drive that home, this is a function which takes a singular input, which comes from this getLine, and then I'm using that input, which is I've named, in two different places. And I guess even, really, in the prior sense, like when we're doing this madness, or even just this. I'm not really, I guess the only difference here is I'm not naming the input. Like I could still just do S, input string line S, and this would be the exact same thing. Yeah. So, and then this next function here, what does this guy do? So we look at the info monad. This is really simple, and even like the type signature kind of tells you what it does. It basically, this will run MA and then run MB and return the result of MB. And so, like, really what we're doing with monads especially is we are just modeling how piping, piping in the sense of like literally, one function to the next, to the next, to the next, like how you might think of like piping in JavaScript or any other language. But the difference here is that we're piping in a context. And so these are really just two operators to define how memory should be passed down the pipe. And so, in the case of where we had here, what this is saying is, so put string line will evaluate, it will run, and it will, it'll create its output, and it will return that unit. And that unit, will end up having, right, like the unit, I don't know, there's no real way to model this. I mean, I guess we have X, where X is of the type IO unit, just for the sake of visual, right? X is of this type, and we have then Y, which is also of the same type of, again, this is not valid here. This is like not valid Haskell code. This would be valid Haskell code, but it's also just like there's no definition for X and Y. But if we had X and Y being these types, then we would evaluate X, toss out the value of X that was returned, and then continue on with Y. So it would not matter. In this case, we're saying it does not matter what X returns. We just will continue on and, work on Y, or evaluate Y and return its results, more formally spoken. And so, so even too, you will see that the minimal function definition, or the minimal definition that you need to do for monad is just the what we're calling it, piper. There's also return, you might have noticed, but return is literally pure. Like literally every single case ever, return is the same as pure. That's always the case. I think that's even a law in how monad is defined, which kind of seems like a redundant law, but I don't know. Why even have it? I feel like the only reason return even exists is for imperative programmers. So yeah. And if we were to look at the type definition of this, I believe it's literally just like, let's say, action 1, and then we just throw out the argument here and do action 2. So we're just simply, it's almost like deleting the memory in that point of the process, because we no longer need it there. I had to take a quick second because my cat keeps telling me it's feeding time, and it is not feeding time at all. It's actually 2:40. But anyways, anyways, where were we? Yeah. So that's how this is defined. How the the discontinuation operator, I'm going to call it, is defined. And yeah, so now that we have kind of seen how monads actually work, just because that is super important, we can get away from the, I guess, I wouldn't even say that they're ugly, but it's really hard to write programs like this using these as control flows. It's just not like a decent experience. And so now we get into do syntax. And so I could write get line, put string line, or I could write with do syntax, get line, call this x, so I am stripping from get line x, and then I'm going to put string line x. And this is the exact same thing. And just for the sake of completeness. And so, like, in terms of main is not taking in any arguments, but inside main we are doing certain actions which expose variables and then use those variables. And so there's no reason I couldn't and this is going to be annoying, but I'm going to call this main prime so that doesn't cause me right. There we go. And if I run main prime, it's going to ask for one line of input, and it's still Dre. So, yeah. You can hear my cat. So, yeah. That is do syntax, and that's really the last thing there is to say about monads in particular. For the sake of completeness, I will write, the instance of monad for either. So the monad for either, so how we would write this is we have to write this function, and we're going to have write x f. So this would be, and so I can't really unwrap f because f is a function. But this is actually really simple because f applied to x, I know, returns me my MB. And so this f at x here is going to be of the type either e, the type of x. And I'm doing uppercase x just because, I hope I said this in the original types component, but types are always uppercase or start with an uppercase. I could do that. So this is valid in terms of the types, and also just in terms of what we're doing. It is what we want to do. Now, if this was left E, then I believe we just simply do left E. And that's, and this even here is just the exact same thing as functor and applicative for either. And I'm just going to check that I am not off of my marbles. that the monad instance of either is in fact like that. Yeah, exactly. It is quite literally that. So that's really all there is to say there. I could, just for the sake of completeness, to show that monad is not any more complicated. If we were to look at the monad instance for maybe, we would see that it's just x. And arguably, it's even simpler, in my opinion. Because it's always going to be really just f applied to x. And then nothing. We don't care what the function is because we cannot apply it anyways. And so we're just going to return nothing. Quite like how we return left e. Yeah, and and really even like for I/O, just for the sake of driving this home, I/O is going to be even simpler. Like let's say we did have this very nicely defined I/O, and this is not exact. This is not at all how it's defined. To be clear, then our instance would look like this, and in terms of the behavior of the functions that I am writing, this is actually exactly true. So what am I doing? I guess I would say IO A X. F would be FX, and that would be it. There would be even less complexity because it's really just continuing on, and wrapping it. Applying the function which rewraps it. Yeah. So, 1 second. All right. So yeah, and that's all there is to really say about I/O as a type class. I think anything further is really just, you kind of. These are the rules. You kind of learn it from example, by doing projects and really drilling in these concepts. That is all there is to say about the concept itself. I cannot possibly say more, and I think hopefully, I'd be curious to know if this pipe idea kind of helped, and because I am trying to figure out what are the best ways to teach Haskell. So yeah, that said, have a great morning, afternoon, or night whenever you like to code, and happy coding. Thanks again for following, watching, all that stuff. Do please like, share, subscribe, and that's it. Hope you enjoyed.